DC charging is fundamental to enabling fast and efficient energy transfer for electric vehicles, with the Combined Charging System (CCS) serving as a critical enabler of this technology. In this video, we delve into how CCS protocol facilitates seamless communication between the vehicle and the charging station, ensuring a secure and optimized charging process. We will break down the essential steps of the DC charging sequence, including handshake and initialization of charging process, the SLAC protocol, power level negotiation via PWM signals, the transition through various charging states, and the transfer of energy to the EV. Join us as we unravel the intricacies of the technology driving the future of electric mobility. Let's first have an overview of a simplified schematic of a DC charging station, as seen here. This layout reveals the key components involved in delivering high-power charging for electric vehicles. Now let's break it down step by step. Power input section, MV grid. The medium voltage grid supplies power to the charging station. MV circuit breaker, MVCB, ensures protection against overloads or short circuits at the medium voltage level. MV-LV transformer steps down the medium voltage to a lower voltage suitable for the charging station's internal systems. LV circuit breaker, LVCB, protects the low-voltage systems from electrical faults. Power protection and filtering. Surge protection device, SPD, shields the station from voltage spikes caused by lightning or grid fluctuations. Inrush resistors limits the initial current surge when large capacitors or transformers are energized. K1, K2 AC contactors control the flow of AC power by connecting or disconnecting the circuit as required. Power conversion unit. Residual current device, RCD, provides safety by detecting leakage currents to the ground and disconnecting the power to prevent electric shock. Electromagnetic compatibility filter, EMC, reduces electromagnetic interference, ensuring the station complies with regulatory standards. Isolation and phase shifting transformer, IPST, provides electrical isolation and adjusts phase relationships for proper power delivery. Fuse offers overcurrent protection, safeguarding critical components downstream. AC-DC and DC-DC conversion. AC-DC rectifier converts incoming AC power to DC for use in the vehicle charging process. DC-DC rectifier regulates the voltage and current to meet the EV battery requirements, ensuring efficient and safe charging. Control systems. Control unit acts as the brain of the system, managing communication safety checks and power delivery based on EV demands. Thermal management. HVAC, heating, ventilation, and air conditioning, maintains a controlled environment within the station to prevent overheating of sensitive components. Active cooling unit cools down the charging cable or components involved in high-power energy transfer, ensuring efficiency and safety. Charging unit DC contactor establishes or interrupts the flow of DC power to the electric vehicle. CPI, Charge Protocol Interface, manages communication between the charging station and the EV for data exchange, like state of charge and power requirements. IMI, Insulation Monitoring Interface, continuously checks for insulation faults to ensure the system is safe for operation. SECC, Supply Equipment Communication Controller, oversees communication with the EV to align charging parameters and ensure compliance with protocols. HMI, Human Machine Interface, provides a user interface for EV owners to monitor the charging status or manage settings. Each of these components works together to ensure the efficient, safe, and high-speed charging of electric vehicles. This schematic highlights the technology behind the charging infrastructure that powers the EV revolution. For more clarification on DC charging system architecture, let's explain a detailed circuit diagram extracted from IEC standard. This schematic illustrates the configuration CCS Type 2 EV supply equipment as per IEC 61851-23/2023. It details the interactions between the electric vehicle supply equipment EVSE on the left and the electric vehicle EV on the right, focusing on power delivery, communication, and safety mechanisms. On electric vehicle supply equipment EVSE side, we have power components including PEC1 and PE2, power electronic converters. PEC1 handles primary power conversion to deliver energy to the EV battery. P2 may act as a secondary or auxiliary converter for additional functionality. FS1, FS2, FS3 overcurrent protection devices protect the system against overcurrent events, safeguarding components from damage. RS1, RS2 resistors in EVSE used in the pre-charge circuit to limit the inrush current during the initial charging stage. CS1, CS2 capacitances in EVSE provide voltage stabilization and filtering in the pre-charge circuit. AS, ammeter in EVSE, monitors current flow in the EVSE to ensure it remains within safe operating limits. VS1, voltmeter in EVSE, measures voltage at critical points in the EVSE circuit. There is safety and monitoring, which consists of US1, insulation monitoring device IMD in EVSE, continuously monitors the insulation resistance of the EVSE to detect potential faults and ensure safety. SS1, switch or relay in EVSE, controls connections during pre-charge and other operational phases. Communication and control, supply equipment communication controller, facilitates communication with the EVCC and the EV over the control pilot CP line, manages parameters like voltage, current, and safety signals. Point A, the point where the proximity pilot PP conductor is connected to the protective earth. This point ensures proper cable detection and mechanical connection. On electric vehicle EV side, there is power components including battery, the destination for the DC energy delivered through DC plus and DC minus terminals. RV1, RV2, RV3, RV4, resistors in EV perform voltage and current sensing for monitoring and control. CV1, capacitance in EV, stabilizes voltage within the EV. DV1 diode in EV prevents reverse current flow to protect the EV's internal systems. We have control and communication composed by EVCC, Electric Vehicle Communication Controller, communicates with the SCC to coordinate charging parameters, session management, and safety checks. CP, Control Pilot Conductor, a dedicated line for bidirectional communication between the SCC and EVCC. It ensures proper charging parameters, safety monitoring, session initiation and termination. PP, Proximity Pilot Conductor, detects the presence and type of charging cable, prevents charging if the cable is not securely connected. Safety and monitoring, UV1, Insulation Monitoring Device, IMD in EV, ensures the insulation integrity of the EV system to prevent safety risks. SV1, SV2 switches in EV control the connection between the EV battery and the charging circuit. VV, voltmeter in EV, monitors voltage within the EV to ensure proper operation. TV1, TV2, temperature sensors in EV, measure temperatures in critical areas to prevent overheating and ensure safe operation. Pre-charge circuit. The pre-charge circuit is a critical feature in this configuration. It stabilizes the connection between the EVSE and EV by gradually building up the voltage using RS1 and RS2 to limit current. Engaging SS1 and SV1, SV2 switches at the appropriate time to complete the connection. Before diving into the charging sequence, let's start with a brief introduction to the CCS charging system and the connector type. The Combined Charging System, CCS, is a globally recognized standard for electric vehicle EV charging, specifically designed to support DC fast charging. What sets CCS apart is its inclusion of additional communication pins, enabling advanced functionalities such as managing charging parameters and ensuring safety during operation. This protocol is tailored to deliver a unified, efficient charging experience, particularly for high-powered DC fast charging, allowing for quick battery replenishment. For a deeper understanding of AC and DC charging and the broader e-mobility ecosystem, you can check out our detailed video linked above. Now, let's turn our attention to the CCS Type 2 connector, a widely used standard for EV charging, especially across Europe. This connector features a two-part design that supports both AC and DC charging. On the left, you can see the EV socket inlet integrated into the vehicle. It's designed to accept AC inputs through the upper section and DC inputs through the lower section. On the right, you'll find the EVSE, Electric Vehicle Supply Equipment Connector outlet, which plugs into the vehicle socket. The key components of the connector are color-coded for clarity. AC charging pins L1, L2, L3, and PE facilitate single-phase or three-phase AC charging. DC pins, DC plus and DC minus, handle high-speed direct current for fast charging. Communication pins PPCP ensure safety, manage cable detection, and coordinate power delivery. This connector is a cornerstone of modern EV charging, offering flexibility and efficiency by seamlessly integrating both AC and DC charging options for EV users. We are now ready to learn about the CCS charging supply sequence. The schematic represents the legend and diagram of the combined charging system, CCS, communication and interaction during DC charging. It provides a detailed breakdown of the key components, signals, and stages involved in a typical CCS charging process, widely used in electric vehicles, EVs, and charging stations. Let's first understand the key components in the diagram. 1. Power line communication, PLC. PLC enables bidirectional communication between the EV and the electric vehicle supply equipment, EVSE. This communication ensures safe, efficient charging by negotiating voltage, current, and charging conditions. 2. Proximity pilot, PP. The PP line monitors the physical connection of the charging cable and determines its current capacity. 3. Control pilot, CP. The CP manages communication for charging state transitions, e.g., connect, pre-charge, charge, and disconnect. It also handles the safety interlock during the process. 4. Isolation check. A safety feature to ensure no electrical faults exist between the high-voltage system and the vehicle body. Protective earth during the charging process. 5. DC contactors. Switches that manage the flow of DC power between the charging station and the EV. These are controlled to ensure safe power transfer. 6. Lock mechanism. The lock prevents accidental disconnection of the charging cable during the session and ensures safety during high-voltage power transfer. Sequence phases in CCS charging. These will be explained in detail in this video. 1. Unmated, initial state where no physical connection exists between the EV and the EVSE. 2. Mated, the charging cable is connected and preliminary communication starts via the CP and PP lines. 3. Initialize, the system performs diagnostic and isolation checks to ensure safe charging. 4. Cable check, verifies cable integrity and readiness for high-voltage charging. 5. Pre-charge, the system ramps up voltage gradually to match the EV battery. 6. Charge, the main charging phase where high-voltage DC power is delivered to the EV battery. 7. Power down, gradual termination of the charging process to safely disconnect. 8. Unmated, final state allowing safe removal of the charging cable. Safety and monitoring features, which covers 1. Voltage and temperature. Monitoring including sensors track input voltage, VIN, output voltage, VOUT, and temperature, TATE, to prevent overcharging or overheating. 2. Protective earth, PE, which ensures the entire system is grounded, minimizing electric shock risks. Now let's see in detail what happens in every state of CCS DC charging. Mated T0. At time T0, the CCS system is in the mated state, corresponding to state B1, where the control pilot CP voltage is at 9 volts. In this phase, the charging cable is physically connected to the EV inlet, initiating communication through the CP. The proximity pilot, PP, detects the connection, verifies the plug's presence, and ensures the plug is securely locked to prevent disconnection during charging. The protective earth, PE line is operational, providing a reliable grounding connection to maintain safety. At this stage, the DC contactors on both the EVSE and EV sides remain open, indicating no energy flow through the supply lines. This phase primarily serves to confirm mechanical integrity and prepare the system for subsequent safety verifications. The color coding in the schematic further clarifies the status of the system's lines. The CP line in pink is signifying it is operational but not yet ready for energy transfer. The PP line in green indicates readiness for charging, confirming the physical connection between the EV and EVSE. The PE line in pink is fully active, ensuring grounding for safety. Meanwhile, the DC supply lines, DC plus and DC minus, are in gray, denoting that they are inactive and not in use at this time. Together, these statuses illustrate that the system is conducting preliminary checks and establishing the foundation for safe and efficient energy transfer in the subsequent phases. At time T1, T2, the CCS system transitions to the initialized state, corresponding to state B2, where the control pilot, CP, voltage remains at 9 volts, but a pulse width modulation PWM signal with a 5% duty cycle is now active. This signal establishes basic communication between the EVSE and the EV, indicating readiness for further checks and system initialization. The isolation check becomes fully active during this phase to verify the insulation integrity of the system, ensuring there is no leakage or fault before initiating power transfer. The DC contactors on both sides, EVSE and EV, remain open, and no significant energy flow occurs as the system is still in the preparatory phase. However, the DC supply line voltages, DC plus and DC minus, are monitored, and their levels remain below 60 volts, confirming that no unsafe voltage is present. The lock mechanism continues to ensure that the plug remains securely connected. This stage sets the foundation for the upcoming cable check phase by confirming isolation and establishing low-level communication through the PWM signal. At T3, the CCS charging supply sequence transitions to state C2 where cable check happens. During this stage, the control pilot CP signal operates with a 5% duty cycle PWM, maintaining communication between the EVSE and the EV. The CP voltage changes to either plus 6 volts or plus 3 volt, indicating plus 6 volt the EV is present but not ready for charging. Plus 3 volt, the EV is ready to proceed with charging. According to the color coding in the schematic, the DC plus and DC minus lines, marked in pink, are operational but not yet in energy transfer mode, as the voltage remains below 60 volts, with the DC contactors still open. The communication lines, including CP and PP, are operational and actively verifying system conditions. The isolation check ensures there are no insulation faults in the system, verifying safe conditions. The lock monitor confirms the plug is securely latched, and the proximity pilot, PP, verifies the connection and cable's capacity. This phase ensures all safety and connection parameters are validated before moving to the pre-charge phase. In the pre-charge phase, T5, the charging supply sequence is in C2 state, where the EV sends a pre-charge request to the electric vehicle supply equipment, EVSE. This request contains 1. The requested DC voltage, which matches the EV's battery voltage. 2. The requested DC current, limited to less than 2 ACE to prevent inrush current during the voltage alignment process. The EVSE responds by gradually increasing its output voltage, VOUT, to align with the EV's internal voltage, VIN. This step ensures that the voltage levels are synchronized before high current charging begins, protecting both the EV battery and the charging station components. DC line status. On the EVSE side, the DC plus and DC lines are green, indicating they are ready for charging. On the EV side, the DC plus and DC lines are blue, meaning high voltage is present but not yet flowing through the system. Communication and monitoring. Control pilot, CP, and proximity pilot, PP lines remain operational, facilitating precise communication between the EV and EVSE. The isolation check ensures no electrical faults or leakage. The lock monitor confirms the charging cable is securely connected. This careful synchronization ensures a smooth and safe transition to the charging phase, which follows once the voltage alignment and system readiness are confirmed. This phase ensures that the EV and EVSE are safely synchronized before the main contactors close, setting the stage for full energy transfer in the next phase. At T6, DC supply adapts DC output voltage stays within tolerances and limits current to maximum value of 2A. In the pre-charge phase T7, the EV ensures proper voltage alignment before initiating high current charging. The EV monitors the difference between the EVSE output voltage VOUT and its battery voltage VIN. Once this deviation is less than 20 volts, the EV commands its internal disconnecting device, e.g. DC contactor, to close, establishing a direct electrical connection. During this phase, the DC plus and DC lines are shown in blue on both the EVSE and EV sides, indicating the presence of high voltage without active current flow. Communication between the EV and EVSE remains active through the control pilot, CP, and proximity pilot, PP lines, which are depicted in green. These lines ensure continuous monitoring of system parameters, while the isolation check and lock monitor verify the system's integrity and secure connection. Meanwhile, the EVSE gradually adjusts its output voltage, VOUT, precisely match the EV's battery voltage, VIN, ensuring a safe and smooth transition to the next phase, where full energy transfer begins. At T8, EV sends power delivery request to enable DC power supply output. After DC supply gives feedback that it is ready for energy transfer, EV sets DC current request to start energy transfer phase. At T9, EV is initiating message cycles by requesting voltage and current values. Supply equipment, EVSE, is responding with voltage and current adjustment, as well as present limit and status values, voltage, current, isolation. Continuous monitoring of lock, isolation, voltage, current, and temperature is being carried out as before. In the charge phase, T10, As the EV approaches the desired state of charge, it begins reducing its current request to ensure a controlled and safe completion of energy transfer. The EV communicates this reduced current demand to the electric vehicle supply equipment EVSE through the control pilot CP line. The EVSE follows the new current request with a slight time delay and gradually reduces its output current IOUT to less than 1A before fully disabling the DC output. Throughout this process, the DC plus and DC lines remain blue, signifying active high voltage operation, while communication lines like CP and PP stay operational in green to monitor the system's status. At T11, after ensuring that the current is below 1 amps, at disconnecting point on EV side, the EV opens its disconnection device. EV then sends a message to DC supply to disable its power output. At the power down phase, T12, the electric vehicle supply equipment EVSE disables its DC output after confirming that the EV no longer requires energy transfer. The EVSE opens its internal DC contactors, isolating the DC plus and DC lines, and fully de-energizes the system. The DC plus and DC lines turn to a non-energized state, signifying the absence of high voltage. Meanwhile, the communication lines control pilot and proximity pilot still remain active to ensure continuous system monitoring and confirm the safe disconnection process. This phase ensures that the EVSE and EV are safely powered down, concluding the charging session securely. At T13, DC supply reports status code not ready with a message to indicate it has disabled its output. In the power down phase, T14 to T15, the EV transitions the control pilot CP state to B after receiving confirmation from the EVSE or after a timeout period. This indicates that the EV has completed the charging session and no longer requires power transfer. Optionally, the EV may perform a welded contactor check to ensure its internal contactors have fully opened and are not stuck in a closed position. During this phase, the DC lines remain de-energized, and communication between the EV and EVSE persists via the CP and proximity pilot PP lines, which continue to operate to monitor the system's status. This step ensures a safe and complete disconnection, finalizing the charging process. In the power down phase, T16, the EV unlocks the charging connector after confirming that the DC output voltage has dropped below 60 volts, or the energy level is less than 0.2 J, ensuring safe disconnection. The proximity pilot and control pilot lines facilitate this final communication, while the EVSE continues isolation monitoring as per its DC supply strategy to verify no residual current or fault conditions exist. The session ends with the EV sending a session stop request message, after which digital communication through power line communication is terminated. The connector is then unlocked, completing the charging session and allowing the user to safely unplug the charging cable. This phase ensures a secure and orderly conclusion to the charging process. In the unmated phase, T17, the EV and EVSE complete the disconnection process. The EVSE ensures the DC output is disabled, while the lock mechanism is released, allowing the user to safely remove the connector. Upon disconnection, the control pilot state transitions from B to A, indicating that no vehicle is connected. During this phase, all power line communication is terminated, and the EVSE ends isolation monitoring. The system is now in a non-operational state, with all high-voltage paths de-energized, ensuring safe handling for the user and readiness for the next charging session. In this chapter, for a better understanding of DC charging process, we'll explore the detailed message sequence for an ISO 15118-2 DC charging session. We'll go through each step in the flowchart and align it with the corresponding charging states, from state A to state C. By the end, you'll have a clear understanding of how electric vehicles and charging stations communicate throughout the charging process. Let's get started. State A, unmated flowchart reference. No messages exchanged in this state. This is where it all begins. State A, the EV is not yet connected to the EVSE, and the control pilot CP line alternates between plus 12 volts and minus 12 volts. This signals that the EVSE is powered on and ready for a connection. Once the EV is plugged in, we transition to State B. State B, plug present flowchart sequence, communication setup sequence. Now we're in State B, where the EV and EVSE have successfully mated, and the CP voltage shifts to plus 9 volts and minus 12 volts. This triggers the start of the communication setup sequence in the flowchart. 1. Supported Application Protocol Request Response. The EV sends a request indicating the protocol it supports, such as ISO 15108-2. The EVSE confirms compatibility by responding with its supported protocol. 2. Session Setup Request Response. This step establishes a secure IP-based communication session between the EVCC, Electric Vehicle Communication Controller, and SCC, Supply Equipment Communication Controller. 3. Service Discovery Request Response. The EV queries the EVSE to discover available charging services. 4. Service Detail Request Response. The EVSE provides detailed information about these services, such as pricing and supported features. 5. Service and Payment Selection Request Response. The EV selects the desired charging service and payment method, like contract-based or ad hoc payment. 6. Contract Authentication. If the EV uses a contract, authentication is performed to ensure the credentials are valid. Optional steps include certificate installation or updates if required. Finally, we have the Charge Parameter Discovery Request Response, where the EV sends its charging parameters, like Vmax, Imax, and Pmax. The EVSE responds with its own limits, ensuring both systems are synchronized. Once all parameters are agreed upon, the EV transitions to State C for charging. State C, Charging in Progress. State C1, Cable Check Flow Chart. Sequence, Cable Check Request Response. In State C1, the system performs a safety verification before starting power delivery. 1. The EVSE first performs an internal insulation test. 2. The EV requests a cable check. The EVSE temporarily closes the DC plus and DC minus relays, and since the EV's contactors remain open, there should be no current flow. This ensures the cable is intact and safe for charging. State C1, Pre-charging Flowchart Sequence. Pre-charge Request Response. Next, we have pre-charging, where the EVSE starts applying a low voltage to stabilize the circuit. 1. The DC plus line is opened, and the DC minus remains closed. 2. The EV monitors the voltage and signals readiness to transition to full power delivery. State C2, Power Delivery Flowchart Sequence. Power Delivery Request Response. Now we enter State C2, where actual power delivery occurs. The EV sends current demand requests to the EVSE, specifying the voltage and current it needs. The EVSE adjusts its output to match these requirements, ensuring safe and efficient energy transfer. This process repeats in a loop to accommodate dynamic battery charging needs. End of charging flowchart sequence. Power delivery, welding detection, and session stop. Once the charging session is complete, the system begins to power down. 1. Power down. The EVSE gradually reduces the current to avoid abrupt power interruptions. 2. Welding detection request response. A critical safety check occurs here. The system verifies that the contactors are not welded shut, ensuring they can safely open. 3. Session stop request response. The EV sends a request to end the session, and the EVSE confirms it. After this, the EV transitions back to State B2, where the plug is ready for disconnection. Once unplugged, the system reverts to State A, completing the session. In this chapter, we are going to explain the Signal Level Attenuation Characterization, SLAC. SLAC protocol ensures a physical connection between an electric vehicle, EV, and an electric vehicle supply equipment, EVSE. SLAC operates at Layer 2 data link and is defined in the Home Plug Green V1.1 specification. SLAC measures the attenuation between two power line communication (PLC) modules. To ensure communication occurs only between the physically connected EV and EVSE, the SLAC procedure is executed. The PLC modules that demonstrate the lowest attenuation are considered physically connected. In scenarios where multiple EVs are connected to nearby charging stations, crosstalk may occur between the connections. An EVSE will respond to SLAC requests only if it is connected to an EV, State B, and its PLC module is not already linked to another PLC module, indicating an unmatched state. How SLAC works: 1. Measuring attenuation levels across various signal paths. 2. Identifying the PLC modules that exhibit the lowest attenuation. An acceptable attenuation level in PLC modules is generally designed to be around 20 to 30 decibel. 3. Establishing the EV-EVSE connection by confirming that these modules are physically connected. In situations with multiple EVSEs or charging stations in close proximity, crosstalk can arise, which refers to unwanted signal interference between adjacent systems. To mitigate crosstalk, the EVSE will only respond to SLAC association requests if the EVSE is in state B, ready to communicate with a connected EV. The EVSE's PLC module is not already paired with another PLC module. This ensures a robust association process and prevents communication mismatches between neighboring EVs and EVSEs. In this flowchart, the SLAC procedure where Supply Equipment Communication Controller, SECC, and Electric Vehicle Communication Controller, EVCC, are connected via data link has been illustrated. After successful SLAC procedure, PLC module of EVSE and the physically connected PLC module of the EV set up a network. Let's now study the pulse width modulation and duty cycle in EV charging systems, which was mentioned in the charging supply sequence in this video. Pulse width modulation, PWM, is a key communication method in EV charging, ensuring safe and efficient power transfer between the electric vehicle supply equipment, EVSE, and the vehicle. The PWM signal operates at a standard frequency of 1 kHz, meaning one complete cycle occurs every millisecond. The duty cycle, a crucial parameter, is defined as the percentage of on time relative to the total signal period. This can be calculated using the formula. For AC charging, the duty cycle ranges from 10% to 96%, with each percentage corresponding to a specific maximum current the EVSE can provide. For instance, a 50% duty cycle represents 30 amps, while a 30% duty cycle corresponds to 18 amps. A fixed 5% duty cycle is used for high-level communication, HLC, as per ISO 15118 or DIN Spec 70121 standards. In DC charging, the duty cycle is consistently fixed at 5%, with communication handled via power line communication, PLC. PLC supports advanced digital features like initiating charging, monitoring battery health, and safely managing power delivery. Unlike AC charging, PLC is mandatory for DC systems to ensure secure and standardized communication. Voltage states and control pilot signals. The PWM signal also conveys the state of the charging process through distinct voltage levels between the control pilot and earth. 12 volts, state A, no vehicle connected. 9 volts, state B1, vehicle connected but not ready to charge, steady 9 volts. 9 volts, state B2, vehicle connected, EVSE ready to charge, oscillating 9 volts to -12 volts. 6 volts, state C, vehicle ready to charge, oscillating 6 volts to -12 volts. 3 volts, state D, ventilation required, deprecated. 0 volts, state E, fault condition, in example grid issue or short circuit. -12 volts, state F, EVSE unavailable. We trust that this video has provided valuable insights into the CCS Type 2 DC charging system and its core principles. For more informative content, we invite you to subscribe to our channel.